Hello, in this video I want to show you a Blender add-on I made called NodeForge. In short, it lets you write geometry nodes as Python-like code and compiles that code into a completely normal geometry nodes setup. Instead of building large node graphs manually or writing hundreds of lines of code with Blender API, you describe only the actual logic and NodeForge generates the node graph for you. In this video, I'll show how it works. You can also download this add-on on Gumroad. I leave the link in the description. So let's look at an example. Here we have this result and the geometry nodes set up behind it. There is a node group with a few parameters. We can change the values and see how it reacts. And this is what it looks like inside. Nothing seems to be unusual, just a regular node setup with all the logic laid out visually. Now let's see what the exact same setup would look like if it were written in plain Python using Blender API. Here is the script. And as you can see, there is quite a lot of code here, and most of it is boilerplate. It constantly communicates with Blender API, and almost every operation takes 2 or even more lines of code. You can imagine how quickly code like this grows once the setup becomes more complex. It is still readable, but with all these boilerplate around, it becomes really hard to see the actual calculations and data processing logic. So what would this code look like if we removed all those low-level API calls, kept only the part that actually processes the data, and reduced the geometry nodes boilerplate to a minimum? Something like this script. Let's take a close look. We have several input parameters like geometry, rotation, scale, count, and height. Their values come from the node sockets and are then processed and used in the calculations. Here we create points, then get the index of each point and calculate the interpolation value, essentially a normalized delta. Next, we calculate the angle of each point along the spiral and the height of the spiral. Then we calculate and set the position of every point. After that, we calculate the size and rotation values used for the instances, and then place the instances themselves. And this code is enough to describe this shape with points arranged in a spiral and instances placed on top of them. And most of the script is the actual computational logic, while the boilerplate is kept to a minimum. It is also much shorter, 33 lines instead of 194. And actually, this geometry nodes setup was generated directly from this script. And that is exactly what my add-on does. It takes this Python-like code and compiles it into geometry nodes. And the result is a completely normal node group. Technically, this add-on is a DSL, or domain-specific language. In other words, it is a language designed for one specific task. And in this case, the task is very specific, writing high-level logic with Python-like syntax, using basic constructs, operations, and functions, and compiling that into geometry nodes graph. There is a syntax processor that recognizes and handles methods, expressions, entities, contexts, character sequences, and so on. Then there is a compiler that translates all of this into geometry nodes entities and builds a node graph that performs the same operations using geometry nodes logic. So it takes care of the repetitive technical work involved in creating nodes, building links, and constructing the overall graph. The user only needs to describe the logic, calculations, high-level operations, and the desired result. Now, let me show you how the add-on works in a little more detail. I will write a short script in this DSL from scratch and go over some of the available features. So at the moment, NodeForge uses a system where the library contains a directory called functions. This directory stores function written in the DSL, and you can reuse them anywhere. So to use a function from the library, you first need to import its name into the script so the compiler can recognize it. If you are familiar with Python, this concept should be familiar. So I will create a new text file, and you can write from functions import followed by some function name, for example, grid points. And this explicitly imports only the function we need. Next, we want to be able to pass in some geometry, so we need a geometry socket. We create a variable with whatever name, I will call it geo, and inside this variable, we store whatever comes through the socket. We create a geometry type socket using the input geometry method and call that socket, for example, geometry. Now we can compile this script and see what it creates. I will go out of this node group and open the N panel with my NodeForge UI. Then select here the text file, which I will call, for example, example. I will press compile script, and the node group has been created with one input socket and one output socket. And if we go inside, there is nothing particularly interesting here yet. Now we need to arrange some points in a grid and add a few extra parameters so we can change the shape interactively. Since we're creating a grid, it needs rows and columns to define its dimensions. We create a variable called rows and use the input int method and call it rows. Then we add a columns variable, also using input int method, and call it columns. We also need a scale parameter, and this will be a floating point value, so we use input float method and call it scale. We can also define the default values. So for example, for rows variable, we can write default, for example, 5, and the same for columns. And for scale, we can write, for example, 1.0. And we also need a spacing parameter, and this would be another float value. Now let's arrange the points in a grid. There are two ways to do this. We can write all the calculations manually. If you are comfortable with math, you can describe the entire setup as mathematical expressions in the DSL. I will show how that works later, but if you are not especially good at math, like me, and you know there is already a function that does exactly what you need, you can simply use that function. And in this case, by accident, There is one called grid points. And because it is a function, it has input parameters. You can think of a function like a node. Almost every node has input sockets and output sockets. And the input sockets are the parameters accepted by the function. And in the case of grid points, some of those parameters are count, spacing, and centered. And also, each socket has a type. There are material, flow, geometry, vector. So when you connect two nodes and the type of data you pass does not match the type expected by the socket, you get an error. The same applies here. So you can think of grid points like a node with a count socket that expects a vector type of data. So we need to pass a vector. I will create a variable called PTS and call the grid points function. And for the count parameter, I pass vector type data. In this case, the count defines the number of rows and columns. So we create a vector and pass in rows and columns as x and y, and z will be 1. The spacing parameter also expects a vector. And let me rearrange a little bit. So we create another vector and pass in spacing, and 0. And the final parameter is centered, which is a Boolean value, and we can set it to either true or false. I will choose true. So this function creates the points, arranges them into a grid, and returns the geometry. And we store the result in the PTS variable. Now all we need to do is place instances on the point on these points. There is a method designed specifically for that, called instance on points. And its name and behavior are similar to the geometry nodes node that does exactly the same thing. We create another variable, type in instance on points, and we pass the geo variable, which stores the geometry from the geometry socket. Then we pass in the points already arranged in a grid and set realize to true. Realize parameter basically defines whether geometry will be realized or not. And the final method is an output, and we call it output and pass in the resulting geometry. So the out variable contains all the instances, the complete resulting geometry, and we expose it as the output value of the node. Now the script is ready. Let's compile it. I will select a node I created earlier and click to update selected node group. And an error appears, so let's see what it says. Okay, I misspelled this default parameter. Okay, finally. And also I forgot to pass the scale parameter for the instances. Okay. Now the node has been updated and it has new values, new sockets, and we connect it to the geometry output along with geometry input. Now the instances arranged in a grid, and we can dynamically control the number of instances or the number of points, as well as scale and spacing. We can also add another parameter, for example, z. I will make another variable with input int type method, call it z with the default value of 1. Then I pass in this variable here to the count parameter, and then replacing the 0 value for spacing vector. So now I will update the node. I see the Z socket appeared, and then when I add something here, I can see how all of this is affect the result. And all of this took 18 lines of code, at least in this script. Now let's look at what was created internally. The script generates a node group, and we can go inside and inspect the geometry nodes setup. Now, the layout is not especially clean right now, but we can use another add-on to arrange nodes, which is called arrange. And this is what the setup looks like. Here we have combine XYZ nodes, then we have instances and points, realize instances, and also the grid points node group. So the grid points function also generates its own node group. And this is what I meant earlier when I said that you can think of a function as a node with input values, input sockets, and output sockets. And inside it, there is another setup that performs some calculations and create points. And there is also another node group called layout grid, which contains its own calculations. And this method defines the grid structure of the points and placing them in a grid shape. So the layout grid is also a function written in the DSL and is used in the grid points function. And that is why grid points has the layout node group inside of it. A number of functions already exist in the library, and you can browse the entire function catalog through the UI. In the NodeForge UI, there are several sections, including local functions and examples. And the functions section contains the full list of functions written in the DSL. So you can select any of them and press Add Node Group, and then the corresponding node group will be selected with its own node graph. And you can also find here a layout grid node group, as well as the grid points node group. And also, you can use them by importing them in the same way I did in the script. And also, you can save DSL functions and scripts you made yourself locally. So, for example, I have this script, which I will call, for example, grid cube. And I go to the local section, select the node group, press save to local. And here I have two options to save either a script from text block or from the selected node group. And then I name this script somehow and press OK. And now this grid cube script appears in the list. And by selecting it and pressing Add Node Group, I can create another node group that functions exactly like the one generated by this script. And one of the most interesting features is that you can reopen the code used to generate any node group from these DSL scripts. So the script is stored inside every generated node group. And you can select a node, choose the text block file, and then press load script from selected node group. And then this script that generated the node group and the entire setup will appear in the text file. So here you can essentially see how the grid points function is written in the DSL. And just how I said earlier, it uses the layout grid function. And so we can look at how the layout grid is written. And the layout grid, on the other hand, is written with plain mathematical expressions. So the mathematical expressions are used to arrange points in the grid structure. So I don't want to make this video too long. I will mention just a few final things. And meanwhile, you can take a look at some of the examples I have already made with this DSL. There is a lot you can do with this add-on and with this kind of workflow, and personally it makes my work much easier. At the moment, the add-on does not cover every single geometry nodes feature because there are many of them, but most important foundation is already done: the compiler, syntax processing, and package management. That means you can write or install third-party libraries for this DSL and use them as you would in any other programming language. I have also written a few additional libraries, one that covers many basic mathematical operations and works a bit like Python's math library, and another for L-system. If you don't know what an L-system is, I recommend reading about it in simple terms. It is a rule-based system that can be used to describe branching and tree-like structures. There is still much more I could talk about, but then this video would become too long. If you are interested in a deeper look and at how it works and what else you can do with it, I can make another video. If you have any ideas, suggestions, or questions, feel free to leave a comment below the video. You can download this add-on on Gumroad. I will leave the link in the description along with the documentation for this add-on. Thanks for watching.